Everybody, thank you for joining us. For some strange reason, my camera has decided not to work. So I am Anita Grove. I am with the Apalachicola National Estuarine Research Reserve, and we host a monthly SciCafe presentation the fourth Thursday of the month. Generally, it's from 3 to 4. The series offers information about science being conducted in and around Apalachicola Bay and in an informal setting to bring together residents and scientists to learn from each other. Our program today will be about an hour in length, and we'll have plenty of time for questions at the end. Today with us we have the Apalachicola Riverkeeper is doing a slough restoration project, and they're going to tell us all about it. I'd like to introduce Georgia Ackerman, who is the Riverkeeper with the Apalachicola Riverkeeper and the Executive Director. Well, without further ado, and she'll introduce our speaker. Take it away, Georgia.
Hey, everybody. Is my sound okay, Anita?
Yes, you sound great.
And like you, I can't see my camera, so I'm just going to hope that all this technology is in place. I see Ken, so I'm going to wave to Ken Jones, a project manager and engineer on the slough restoration project. I'm Georgia with Apalachicola Riverkeeper, and I just wanted to take a moment to tell you a little bit about Riverkeeper, and then Ken is going to provide you with an in-depth overview of the slough restoration project that's currently underway and funded by the National Fish and Wildlife Foundation. Apalachicola Riverkeeper, if we can jump back to the other slide, is part, or the next slide, forgive me. The Apalachicola Riverkeeper is part of Florida Waterkeepers, and we're part of the International Waterkeeper Alliance. We're an independent nonprofit organization, and in a nutshell, our job is speaking up on behalf of the health of the Apalachicola River and Bay. So we do these things, and we've been involved as an organization for over 20 years now in the Apalachicola Basin, which of course you all know is part of the broader Apalachicola Chattahoochee Flint Basin that is shared by 3 states. Our programming includes outreach and education, advocacy at the state, local, and national level. Legal action is also part of what we do. Collaborative research is a big part of our history as well. And then as you're going to hear from Ken shortly, we're also involved sometimes in direct restoration efforts. And this is a project we're really proud of and excited about. Ken Jones oversees the slough restoration project, and we'll tell you more about the 3 sloughs and focus in on East River today, as I know folks are eager to hear about that as well. And Ken has an extensive background. He's no stranger to the Apalachicola Bay and his coastal engineering background. He has spent a lot of time in and around the river, and also worked for years with the Northwest Florida Northwest Florida Water Management District. So without further ado, I'm just going to let Ken take it away, and then we'll also both be around to answer whatever questions you might have about either the project or the work that Riverkeeper does. I would encourage you, if you'd like to stay up to date on the project, visit our website. It's apalachicolariverkeeper.org, and you can get signed up for direct email updates as well there. So thanks all for being here, and thank you for hosting us at the SciCafe today.
Well, thanks, Georgia, and thanks, Anita, for inviting us to come and speak with you. It says, when ready, I'm the presenter, show my screen. So I'm presuming you're seeing our cover sheet for the project. We're going to talk about slough restoration in the lower Apalachicola system. The project was funded by the National Fish and Wildlife Foundation, part of a lot of the BP funding streams that have helped a lot of folks do research and restoration projects. And as Georgia said, the project was sponsored by the Apalachicola Riverkeeper. They supported the proposal writing and so a lot of the preliminary work that led us to this project. A couple of shout outs to the National Estuarine Research Reserve, who set up one of the monitoring stations that helps us look at some of the freshwater flows, and they've been a great asset and group to bounce ideas off of. We're also working with co-ops, the Center for Oceanographic and Atmospheric Prediction Science, and they're the modeling group with ABSI, and the University of Florida Milton offices houses some of our researchers. So how do I advance this?
You should be able to just click ahead like you would normally with a PowerPoint presentation.
Oh, there it goes. Maybe just took a second to jump. So slough restoration has been, on the docket for years. The Water Management District has included it in swim plans, and it's been a high priority for the Fish and Wildlife Commission. There's about 20 slough systems in the lower Apalachicola. We did, the Apalachicola Riverkeeper did a number of studies a few years ago that really discussed the geoformological changes, the movement of sand and sediments within the streams themselves, and documented just the choking off of a large number of streams within the lower system. We picked 3 streams to begin with. Douglas Slough, which is a pretty short, pretty simple project where just the mouth has been closed up by sands. Spider's Cut, which is a longer system, about a mile long, that flows into about a 2,000 acre floodplain area. And then East River, because of its importance, is it relays fresh water to East Bay. So it's a large team. Matt and Scott at the top of the list here, all from the University of California, and they did a lot of the early research. AJ Sharma has done a lot of work in Tate's Hell, and he has a new graduate student who's doing a great job for us out looking at the floodplain work, and actually going back and reanalyzing a lot of the work that Helen Light had done and updating that work for his PhD, which will support our project and the benefits of our project down the line. And then our engineering team, including Dan Tonsmeyer, I know a lot of you all know, the past Riverkeeper, and he's really a lot of the energy that keeps us going. Michael Gangloff doing the mussel work in the rivers, which is really important, and Andrew Gannon, who's been doing blue crab work down in East Bay for a long time. And also just to note that the National Wildlife Federation and Melissa Samet helps us with policy and permitting. So I'm talking about Spider's Cut first. It's an interesting system. The white square up there is our project area, and it's about 4 miles between the Chipola River, which connects to the Apalachicola right here, and the Brothers River. And so water traditionally flowed down this stream system and spread out throughout this about 2,000 acre floodplain basin. So a little closer look, this is our survey data overlaid on the recent LIDAR data that's out there. Some interesting things about the project. So Spider Cut, you can see it in the middle with all the colors where we did our surveys. That's the bathymetric chart that we did for there. Little Spiders is just to the west of us. And the interesting part about Little Spiders is it did not get clogged up. So it's pretty much a free-flowing stream, and it connects into Spiders down at the bottom of where we did our survey work. And so part of what we're doing is looking at, potentially what caused Spider's Cut to completely clog up and Little Spiders to stay relatively open. But doing this project in Spider's Cut will actually allow us to at least double the amount of water that is distributed out of the Chipola in the Apalachicola system and down into this floodplain system. Now, the work that we're really concerned about, or the time periods that we're really concerned about, are low flows. Once the river system gets above about 16,000 CFS, the river overflows the bank and floods the floodplain, and that's the way it's done naturally for years and years and years. And once it gets to that level, everything pretty well fills up and floods, and it acts like a floodplain, and it does what it's supposed to do. Below 15,000 CFS, which is the low flow period, down to about 5,000 CFS, which is considered generally the lowest flows we should be getting in the Apalachicola. The floodplains are cut off by the river berms, and so the only way that they can become hydrated, and this usually happens in the summer, is through these slough systems. And so when these slough systems get clogged up, either through excessive sediments in the river due to dredging or spoil deposits or whatever caused a specific slough to clog up, it keeps the water in the main stem of the river, and it doesn't allow it to flow into the floodplain to hydrate the system itself. And there's two problems in that. One, the floodplains need a surge of water in the summers and the hydration that they get from that. And two, these areas act as huge sponges, collecting water for when the water is distributed down in here, and then slowly metering it out further down to the bay. If it stays in the main stem, you get that shot of fresh water down through the system pretty quickly, and then that's all you get. When it gets to be dispersed into the floodplain itself, it spreads out. It still makes its way down to the bay, but it makes its way down to the bay over a longer period of time, which is beneficial to the freshwater regime in the bay itself. So just to give you an idea, well, let me go back here. This picture up in the right corner was taken about 2016. And this is the mouth of Spider's Cut. And you can see the sand deposits. The water's really low during this period of time. Water cannot get back into the bay. This was all part of the original studies that were done. And just a few short years later, this picture in the right corner behind the boat is that same area. This shows the water's actually a little higher. This is a big mound of sand in the middle, and all of this volunteer willow growth continues to clog the head of Spider's Cut. And so the arrow's pointing to this little area, this triangular area here, where we're getting where it's being cut off by from the Chipola River. These are contours from surveys that we've taken. The red dots are locations where mussel surveys were conducted, and these targets right here where we did soil corings. And so you can see how clogged this area is up here. And to give you an example, based on our calculations, we predict 5,000 CFS would be around somewhere between 2 and 3. So in here, these contours indicate that would be completely cut off from the Chipola River at that level. And even at higher levels, up to 10, 12, 14,000 CFS, we're only getting a trickle of flow in through this area here and this area here. Part of the project will be to completely clean the head of the stream out through dredging and removal of these willows to reopen this part of the stream itself. The contour map shows this purple area right here. These are deeper areas where there's still a little bit of organics. We did find some mussels down in here, and part of our strategy is basically to leave these refuge areas alone and to do the excavation in where the sand plugs are. So here's a couple more pictures in lower flows. This is all volunteer grasses. A lot of willows, birches that are in this area that we're looking at. We obviously want to do as little amount of excavation as possible up towards the banks and cut out as little amount of vegetation as possible. But all of this has been deposited, and because it's opened up along the string bank, you get these grasses and these volunteers to grow. This is a little farther downstream in the left corner. I'll give you an idea of how shallow this system is going through here. This picture is interesting because if you can follow my cursor, the historic channel moved up and around this oxbow right through here. That's completely been clogged, shut down, and clogged off, and just through natural processes, at higher flows, water has broken through this section and has started to reform the stream down through the middle, right through here. We won't go back and try to reestablish this, but follow the way the stream naturally went through this area. A little further down, you can see in low flows the amount of sediments that have built up along the sides. You can see all the borings that we have taken. It was pretty amazing to me as we did the vibrocores in here, how much sand was in this material. Very, very little silt, hardly any clays at all, well over 90% clean sands uniformly throughout the system. That's it. That's an indication that it's not natural, that it happened pretty quickly. You're not seeing any real organic buildup in any of these deposits through here. A little further downstream, this is almost to where we reconnect into Little Spider's Cut. This picture was taken about 2 weeks ago when we were out surveying. You can see there's less than a foot of water through here. This area used to be passable by boats, and when you measure the water depth in Little Spiders and Logjam, which is the slough to the east of here, water level and bottom of stream levels are 5 feet below this elevation. So part of what we're doing is trying to figure out how much material we want to dredge out. And as I said, we took a cross section. So right through here, if you look right across here, here's a survey of that area. And this line right here is the existing grade, existing ground levels it goes through. So here's the bank over here and over here, and then the floodplain stretches out from there. Looking at the bottom of the streams on both the Little Spiders and Logjam, somewhere around 1.5 is the bottom of those streams. So if we pick that as the bottom and we put a template over top of that, making sure that we come far enough inside from the edges of the bank so we do not disturb the trees, we do not disturb the root systems, we don't want to impact any of the habitat value within the stream itself, but we want to come well inside of that. You're looking at about a 5 foot deep section that we would cut away. And when you're looking at the math, that turns out to be about 4 cubic yards per foot, which is pretty consistent with what we estimated early on when we did the grant application. So that was kind of nice that our really back of the envelope calculations seem to coincide pretty well with what we put in the grant, which means hopefully the funding for this excavation is going to be consistent with what we're hoping to do once we get the plans done. So here's another one of the big problems in spiders, Hurricane Michael. Here's a number of the photographs from that first photograph. If you remember, there was nothing in the stream. One of our big struggles we've had is to be able to get back in to do surveys. We've had to cut our way back through fallen timber, and this will be an added problem for us as we start to look at how we're going to bid and do this construction, because all of this down timber is going to have to be removed so that we can get a suction dredge back in here and cut this material out. It's an amazing amount of material. I've talked to a number of other counties that have these sluice systems, and they report that these kind of problems exist in all of their streams, and they're desperately looking for help to figure out how to at least get the vegetation out of there to let the stream start to act normally again. So huge problem we're dealing with, both on the survey and engineering side of it, but one we're going to have to deal with once we get to construction itself. So why are we doing this? Helen Light and Melanie Darst have done a lot of work over the last 20 to 30 years in looking at cypress tupelo swamps. The decrease in flows into these swamps have caused a huge decline in the swamp species. Part of the work John Tracy and his PhD is going to be doing is to extend this data set out to the present, and look and see where we are today. But this is just the slough restoration that we're doing is just a tiny piece of the entire puzzle to look at the restoration and the rehydration of the floodplain itself. So let's talk a little bit about East River. This is a digital elevation map that was developed by NOAA. This is the map that the ABSI people have started with to do their modeling. And as I said before, we're collaborating with them because they're doing this huge modeling exercise. There wasn't a lot of value for us to do this independently. And so we collected all of the data for the modeling within this part of the system to help them with the boundary conditions and the geometry for their model. So some interesting things, and I know a lot of y'all know this, but you know, the Apalachicola and the main stem down through here takes a significant amount of water, but it's really not well understood how much of this water is diverted through these distributaries. There's a huge amount of water, and a lot of you, I'm sure, have been up to the St. Marks, where the St. Marks cuts off the Apalachicola River. But this is a big river that pulls out of here, and it could be as much as 30% of the total flow of the Apalachicola River, and at times even more, potentially at lower flows, that's diverted out of the St. Marks or out of the Apalachicola into the St. Marks, and it either runs down the St. Marks River this way, or it comes through the East River cutoff and then heads down to East River here. What we're interested in is, and this is a telling map, because this is the map that says this is how deep these creeks are. And so East River comes up right here through here, and you can hardly see it, but that little line right through there is NOAA's depiction of the East River, and it obviously is showing it's clogged up. A lot of this is trees that are hiding the LiDAR and such. But here's where the East River comes in. It's about 14 miles above the mouth of the Apalachicola, and it feeds down through here, and then it comes down into the East River system. Now, the goal here is that if we can open this section of the river up, we might be able to get a significantly greater amount of fresh water into the East River portion of the distributary and deposit that fresh water up here in the Blunt's Bay region of East Bay. And all the science has indicated that the higher up in East Bay you get, you want that to be as fresh as possible, because that's the highest productivity areas for East Bay itself. So if we can open up East River And if the work we do demonstrates that that actually generates more fresh water into the northern portion of the system, then that's a huge benefit. So to give you a little perspective, here is the project area that we're working in. That 2.5-mile stretch of East River is completely choked off. The water has to get, water always flows in it, but the significant amount of that water is reduced, especially at low flows. And just from a perspective, like I said, this is 12 or 13 miles from the head. From this point on in the East River is deep. It's a minimum of 10, 12 feet. Often it's 20 or more feet all the way down to the end. So that the fact that this area is so shallow, tells you something that's going on that's not natural. So the distributaries are so dynamic and they're really, really interesting. And so this is some of the stuff that is happening today. So this is the St. Mark's River that comes down. It flows around this oxbow down through here, and it comes back and it comes very close to the Little St. Mark's. Well, this region right through here is broken through. It's a natural process, and it in a lot of oxbow systems, it's come back on itself, and it's broken through. And now what's happened is the river is starting to change its form. So because this went so much further, this area down here is lower, and the water that's coming this way wants to shoot across, and you can see it if you look over here. This is the Little St. Mark's, and this water is actually reversing and shooting and coming back this way. And I think what you're starting to see, at least anecdotally, is this region of the Little St. Mark's is starting to shallow up, and this is becoming more of a major the major artery through here. So it'll be interesting to see how this plays out. Another place that we've been looking at, and this is up on the East River, and as we're looking at how do we get as much fresh water down East River as we possibly can. This is the old rail system that went through here back when they were doing the logging and such. And here's a picture of that rail system. And what they did is they cut right through the bank. I don't know, 100 years ago, when the 1920s, actually it was probably the 30s or late 30s, they cut right through the bank and ran this trestle system down through there. Well, that's created a large creek, and at different tides, you can see a huge amount of water being diverted out of East River and down through this creek system, which ultimately gets into the St. Mark's River. So just an interesting thing as one part of the river opens up, other parts close, and all of them might be worth looking at, or at least understanding how they impact the freshwater delivery into the bay. So here's a picture of the surveys that we've done. We have water quality, water level stations, water level, pH, DO, conductivity. All of those stations are tied to the same datum as the ANR stations. So we can look at water levels here and compare them directly to the Butcher Pin station that ANR built for us, or the NOAA station down in at Apalachicola, and these are all tied together horizontally. Interesting part, here's this is our survey data that we collected through here. Again, these circles are where we did borings. The background is LIDAR. That was the from that NOAA DEM. You see all this yellow down through here, and it looks pretty definitively that portions of this area have been dredged and spoiled onto this side of the bay, or this side of the river. Another interesting aspect, and you see these cut throughs right here, and we're hypothesizing, and I think it's true, but these were where they ran the cables out into the forest when they were cutting down the cypress, and they brought it back to the East River, and they cut this section right through here. And this is Graham's Creek as it runs up and it curls back up into the Bloody Bluff in that area where they have roads built. And so they would bring the cypress back through here and then float them up this creek system to haul out of the forest. This is one of the areas we're actually looking at potentially restoring, and we're trying to get some feedback from the environmental groups about if that's a good place to rebuild or deposit sand back into it, force Graham Creek to come its natural way and help us blow some of the sand out of Graham's Creek. So this is all a function of what's living here now and what are we going to hurt if we put the sand in here, or is that a good idea? So we're still working towards that answer. So here's some of the survey data. Here's an area of the shallow reach. It tries to act like a stream, so the outward bends are deeper, which you would expect. We do get flows at higher flows down through here, which creates velocity and causes some scour. So it does mimic natural creek processes, but you get these long straightaways where it's just very, very clogged up and very shallow. Here's some water level data. It's kind of interesting. This blue is the water level at the Apalachicola River, right at the head of East River. This is the station that's 2.5 miles downstream. So it's right where the deep East River and the shallow East River come together. You can see the tidal signal in this area. This tidal signal has propagated up the river, the 11, 12 miles, but it can't make it up the remaining 2.5 miles, probably because of the limits of the sand that are clogging that system. But this gives us an indication of our ability to push water through East River, and you can see that the drop over that 2.5 miles is about 2.5 feet in these lower flows. So if we open that part of East River up, we will be able to push water through that system. So here's just another graph, and I don't want to get too bogged down in this, but the yellow line is the Thalweg, and for those of you who don't know, the Thalweg is the natural course of the river. So this includes where the deep sections are and where the shallow sections are, but it's following the deepest natural course of the river. The blue line is the center line. And so where the blue line and the Thalweg come together, those are good indications that the system is clogged up. Where the blue line and the yellow line are far apart, it's indications where we probably only need to do limited dredging. We've set kind of still a preliminary bottom of slope, which is this white line here, to kind of give us an idea of what we think the depth profile should be of East River. And you can see in the Thalweg, it's deeper, in places downstream or even up here. We don't want to dig the whole thing as deep as the deepest portions. That's not the way streams work. And so we started looking at where we thought basically the bottom of the stream should be as we cut through there. And that's what this line represents. This is the average of the Thalweg, and this is the average of the center line. So these are cross sections. So imagine standing in the stream and looking upstream, and every one of these lines is what it looks like from bank to bank on 100-foot intervals. And here was that shallow section. You can see there's not very much of a stream here. The water level's probably up around 1.5 to 2. So we it's basically 2.5 feet deep through this section. These are sections we'll have the most aggressive excavation in. They'll be the deepest section. This white line is that same white line I showed you on that graph before. So we'll come in here, we'll cut down into that white line, and that template is what we'll end up removing and opening this stream up to that level. On the curves, you can see you have some shallow sections and deep sections as it transitions. Places where the stream are deeper, we don't need to cut. Those are also places where you'll find more organics and more critters like to be in these deeper sections. These shallower sections are just completely sand. And it's sterile sand. There's very little that lives in these areas. And as you get down into these really steep curves, these get a lot deeper. We do a lot less excavation because nature has started to make it do what what nature does. And plus, these are areas that are starting to look natural. We don't want to impact the habitat value of any of these deeper sections through here. So this is just same kind of thing. This gives you an indication of what that section looks like to scale and how big it is. And then these are looking at various different templates with bottom widths to do the excavation. Now we slide these templates back and forth. They don't follow the middle of the stream, but they follow the thalweg to make sure that we reform the stream the way it naturally wants to form. This is the picture of the head, and just like I showed you on spiders, you can see this large area here that is filled in. This is interesting. This area back in here, this green, is the remnant channel from East River. And so this is the way East River used to go. And a long time ago, they cut this direct link into the Apalachicola for ease of hauling logs out of this system. So you can see that if the minor work of removing this little section and maybe this little section right here, not getting into these deep areas, this would open this up down to 5,000 CFS just by itself and create a huge amount of added relief and additional water through here. It would still be dammed up further down, but you would be getting a lot more velocity through here, and even by doing this little amount, you would start to nurture the natural processes that you have in these distributaries. I guess I had these in backwards. So this is what it looks like now. And that's the section we'll end up excavating to reopen this out. This was the natural bank. I say natural after it was dredged. So how are we going to do this? We're looking at a variety of different ways, but I think we're coming pretty close to using these small suction dredges. These are like 6-inch dredges. They take a little longer, but they're only about 8 feet wide, 20 or so feet long. You can get them into these really tight areas to pull the material out. We're looking at some direct restoration projects up by Spiders with Fish and Wildlife Commission, but there'll be probably in the East River, we're going to have to bring the sediments out, and we pump them into these large geotechnical bags and allow the water to seep out. That way we can keep the water clean. There's a couple locations near East River that we're talking to people about, both Fish and Wildlife and some leaseholders about where we can put these bags. This material is good fill material, and the county or others could use it as fill material for project sites. It has value. So it's not full of organics or clays. It's almost all sand. So it does, it can be used in other locations. Once it dries out, we just haul it out by truck. So, part of, I talked about this earlier, but what we're really looking at East River, the East River restoration, is whether or not we can lower the salinity and low flow periods in this portion of the bay. That's the highest level of benefit I think that we can generate. But that's not to say that opening this back up by itself doesn't create a huge benefit just to the in-stream flows and the habitat and the passability of fish and other species to move through this corridor that it doesn't presently have at low flows. So it's not only East Bay, but the in-stream habitat from East River itself and the reconnection of this to the main stem. I said that real quick, I'll just go over this just on some of the modeling. Part of what we want to prove is that the freshwater delivery is greater. We're working with ABSI and the co-ops people at FAMU and FSU, and we did all this bathymetry work in here. Just to give you an idea, this blue line was from the DEM. That it's what they would have used if we weren't out there, or they would have had to collect the data themselves. Here's what that channel actually looks like. You can see it's just huge differences in the data. And ground truthing LiDAR data and DEM data like this is always a good idea, especially when you're trying to really understand very specific processes. Just a couple of the other places you can see up here. This is the lower East River where it's showing 7 meters deep, 21 feet deep, and the DEMs show it, basically flat. As you get further and closer to the bay, it looks a little bit better. But we did all these cross sections to validate this work and have supplied this to ABSI, which I think will be a huge benefit in understanding the delivery of fresh water through the distributaries at both low flows where we're interested, but also in high flows. And here's the model that they're working in, and we're trying to discern the distribution of fresh water across all these distributaries. So this is phase 1. NIFWF actually renamed it phase 1, which I thought was interesting and really, forward-looking from their perspective. We're doing the work in Douglas and Spiders and East River, which is down here a little bit further. But there's a number of sluice systems and sloughs between here and River Mile 89, which is up close to Bluntstown. And all these sluice systems have different levels of impact, largely from the dredging and sediment transport of the river during the dredging periods, and the within bank disposal uses. Some of them are just clogged at the mouths, some of them are clogged well into the systems. And so hopefully, what our goal is to not only do these restoration projects, but we will do surveys of these other sluice systems, and our final report will look at prioritizing these sluice systems for future restoration projects, phases 2, 3, 4, etc., and also provide some guidance on costs and techniques and methodology and permitting issues and all the things that we're going through as we work through the issues of the work we're doing in Spiders, East River, and Douglas Slough. And so that's my presentation. If there's any questions.
Thank you, Ken. That was wonderful. If you have any questions, you can put them in the chat or raise your hand and we'll call on you. Ken, just a quick question. What is the time frame for this first? phase?
So we are, we've completed surveys. We completed surveys in the winter when the low flow was here, and we're collecting water level data and developing the engineering documents right now. We hope to go to permitting, pretty much as fast as we can, and then permitting can last anywhere from 6 to 18 months. So, we'll go through that process just like everybody else goes through. So we would look to begin work probably next year.
Okay, great.
All right.
Well,
I don't have much in the question box, but I was curious, has this kind of slough restoration happened elsewhere? Any other case studies that people might be able to look at?
I mean, they do, there's restoration projects, all throughout the Gulf for a variety of reasons. I don't have any direct context. There's a lot of literature on stream restoration techniques. It's a whole science. And basically Matt Kondoff and Matt Deach, professors at Cal and University of Florida, that's what they do for a living, is stream restoration projects. So they're the principal investigators in this. My role is herding the cats and the engineering side of it. So we talk a lot about how to do this work in such a way that it's sustainable. Part of what we're looking at is we don't want to do this excavation and then have it fill up right behind and have to do this, do it again. There's an art to developing the right section so that you get enough velocity to keep these things, these sloughs flowing and carrying the sediment loads, the natural sediment loads. What happened here is I believe we had significantly man-made sediment loads that clogged these things up. And there's two problems. One, the clogging of the head of the slough, and the volunteer of the willows has made it harder and harder for the sloughs to reopen naturally because it's choking off that piece. If you could just open the heads up, you would probably see them kind of regenerate over time, but it would be decades versus a year. But there is a lot of literature out there on stream restoration and how to do it.
Ken, I just wanted to add, and I apologize, I lost audio for a little bit, so if I reiterate something, forgive me. A lot of folks don't know that, in our 106-7 mile river, we've got over 400 miles of sloughs, creeks, and streams. So this is a really, connected system, and there are a lot of sloughs, and we're hopeful that this project, with its demonstrated success, that will help.
I think we lost you, Georgia.
Yeah, Georgia froze
you froze up.
Yeah, I talked about this kind of restoration we're doing here is very pertinent to the lower, and I say lower, from about 80 miles south, where the floodplain has gotten larger, and there's a lot of distribution of water from the main stem into the floodplain. As you get further north, the restoration falls in a different form. These are tributaries, not distributaries, and they flow into the Apalachicola. And so making sure that you're getting that contribution upstream into the Apalachicola River and providing fresh water downstream is important to make sure that we keep those open. but they're different processes from, you know, the bay up to Bluntstown as they are from Bluntstown north to the dam itself.
Okay, wonderful. If we don't have any other questions, I know Georgia's trying to get in. I don't think she's got the bandwidth there. I wanted to say that I wanted to thank Ken. Thank you so much. Where would somebody go for more information? The Riverkeeper site?
Yes, Georgia keeps a very active site. She puts blogs up on a regular basis. And obviously, if you have any questions, you know, I can, or if you want to, Anita, you can share my email.
Okay.
And or go through Georgia, and we'll be happy to provide you any information on this.
Great. And I did include the site in the chat. And wanted to also thank Josh. He's here with me producing the webinar, and also invite you to future SciCafes. We have one on July 22nd that's going to be about the Tate Hill restoration. And then we have one on in August, which is going to be DeMarcus Turner, and he's going to be talking about some work he's doing with microplastics. And then we'll actually have an in-person SciCafe again after a year or plus. On September 22nd, we'll be at the East Point Brewery, and we'll have an update from Dr. Sandra Brook with the Apalachicola Bay Systems Initiative Project and the neat things that are going on there. So please join us, and thank you for joining us today. All right.
Thank you.
Thanks, guys.
Thanks. Appreciate it.